Hello and welcome once again for another EE324 video. This time we'll be discussing an electromechanical example and we're going to do a classic example with the DC motor, and we'll take the DC motor and put it onto something, a robot arm in this case. Okay, so here's our model of a DC motor. We have the commutator, which is down here. We have a brush, which gets spun by the commutator. We have a shaft. We have rotor windings. And the rotor, and we have a stator magnet. We have a magnet as well. And so the magnet, the whole point of the magnet is to produce a uniform electric field, a magnetic field over the top of the rotor, and the rotor plus the coils that make up these windings here, the rotor plus the coils is called the armature. Okay. So the first thing that we should do is we should think about what happens if we have, say, a wire here that obviously has been coiled. It's in some kind of plane, and I'm going to have I'm going to show the direction of the current in this wire due to B. Now, due to the magnetic flux here, B. Now, and then finally we can actually see where the force is here. So basically what we have is we have a wire moving through a magnetic field, and a current moving through a wire that's in a magnetic field, and when we account for both the current, you can use the right hand rule here. When we account for both the direction of the current and the direction of the magnetic flux, we can then determine which direction the force must be in. Okay, and then the other piece of information here, and I promise this is the last bit. Will be the orientation here. So now we do have this piece moving, and it's moving through a uniform magnetic field here. So it has a velocity in that direction and a uniform magnetic field, and this will be the orientation then, again by the right hand rule. This will be the orientation of the electric potential, the VM. Okay. So what we can write an expression now. I'm trying to make sure that my V's and I should probably put a little thing here. My velocity and my capital V for potential don't run together here. Here's a few facts that we'll have, and these come from standard physics type things. So the potential here is going to be BL times the velocity, where L is the length, right? Of this conductor. So in this case, it's that piece, the length of that piece, and B is the magnitude of the flux, the magnetic flux. Okay. And the force is also going to be related. This I is going to be the current. I'm using capital I here for current. And I'm going to use one more fact. So V, since this is rotational motion, V is going to be equal to theta, well, it's going to be equal to omega times r, which is going to be equal to theta dot times r. Okay? And so, that's just the linear velocity is related to the rotational velocity by this by this relationship that we have here, omega times r. Okay, so that is another thing that comes directly from physics. So combining those facts, then I can write this as BL r times theta dot. Okay, and the torque that we'll be working with for this DC motor, tau m. I'm going to give this a 1 here to just to note that it's the, yeah, well, we don't need that. The torque on a single coil is equal to the force times r. I should write what r is. It's the radius here, right? This is my r. Is the force times the radius, which is equal to BL times I times R. Right? We already said that the torque, we already saw earlier in the other video that the torque is equal to BL times I, and then or the force is equal to BL times I, excuse me. We saw it right here. Force is equal to BL times I, so the torque then is BLI times R. And this is a general expression for the torque, right? If you go back to your physics books, you need a cross product with R, and R is a vector. But we're only going to be dealing with, for this course, we're not going to be dealing with vector parts. We'll just deal with the scalars. So we'll make sure that the problems are for scalars. So what this means is, if we sum the torques, since there are n coils, I should call this something else. I'm going to call this tau. And then this will be my tau m. Okay? And similarly, let's just call this V for the moment. I'm going to get rid of the V, M. I'm going to get rid of the subscript m here. Because what I really want, Vm is going to be equal to n times BL times theta dot times R. Okay, so this is true for, and then we actually will define this constant Ke as n BL times R, because it shows up obviously so many times in the motor. So that just means that Vm is equal to Ke times theta dot, and tau m is equal to Ke times I, where I is the current, remember. So when we put all of this together, this is what we get for a DC motor. These are going to be our equations for a DC motor. So now let's make this into a nice, somewhat complicated problem. Let's suppose that I have the following. So we're gonna have a robot arm that is moved with a DC motor. Okay. So what's our model going to be? Well, it's going to be this. Okay, and also this. So we have this nice little gearbox here. Here we're going to have some we're going to have two pieces that are connected through a gearbox, and this is going to be when we pair this electrical circuit with this mechanical rotational motion. Then we will get our robot arm. Okay. So the first thing we're going to do is we're going to take and analyze the circuit, because that actually is going to be an easy part. You should be able to find this circuit, of course, really easily. This just, if we use Kirchhoff's law and Ohm's law for this part. Now this part is going to be a pain. Oh, and I'm going to rewrite this, by the way. This is going to imply right? We already determined this up here, that Vm is equal to Ke times theta dot. So for us, that's going to be this is going to be the case. Oops, I don't want Ra, I want Ia. The current at the armature. Okay, so we're going to get that part. Now let's look at this part. This part's going to take a little bit longer to do. So the first thing we're going to do is we're going to draw a nice free body diagram. Oh, I didn't give you this part, did I? This is tau m. This is going to be theta m. I'm going to define my direction like this. This direction is going to be theta. Okay. So this is going to be tau m. TD is the D'Alembert torque. Excuse me. For the other one, so this is R1F and R2F are related to the gearbox, of course. And that's how we get our torque there. Our D'Alembert torque. And let's do for the gearbox. We have this little thing, R1, and the force is going to come out that way, along with this bigger one, R2, for which the force is going to go this way. Okay, and obviously those forces are going to balance each other. So let's call this one number 1, this one number 2, so that we can see. For 1, we get the following equation. And this part is the D'Alembert torque, right? And for 2, we get the following equation. So now we'll solve 2 for F, because I'm going to substitute that back in a moment. So what we get is okay. When we substitute this back in, and just like we did before, we're going to let R1 over R2 equal to N, and because of the gear relationship, gearbox, And if you don't remember this, you can go back to the original rotational motion video, because I gave this as one of the types of equations way back then. But in the gearbox, it's going to look like this. And this obviously implies if I take the double dot here, then taking all of those facts, and tau m is obviously our input, but in this case it's going to be a DC motor, so you should be thinking already ahead that we already found an expression for tau m for a DC motor, and since that's going to be our input, that's what's going to go in here, but we're getting there. But first I'm going to do this. Oops. I just, all that I did is combine all the terms there. The input here for a DC motor is equal to KE times I. And in this case, it's going to be times IA because that's our input current, the armature current. And this came from way back up here when we solved for the current. This was our current, right? Our IA was this. And I just substituted that in for tau m and used this fact, okay? And VA is obviously our input voltage here. So that's our equation for this combined system. So it looked kind of daunting at the beginning, but if we work through it, it's not so bad. So now let's find the transfer function of this. I'm going to denote my variable by phi of s instead of theta because my capital thetas and my lowercase thetas kind of look the same, so I think it's just easier if I do it this way. And obviously my transfer function, this is going to be my plant, right? This would be my plant system. In the context of control. And then I'm going to factor out an S here. And notice that there's no S inside of this relationship now. So this should immediately tell you that your system is at best marginally stable, right? Because I can factor out that S. So that means that one of the poles is 0. And then but the nice thing about being able to factor this out is you can easily find the other pole, because you don't need a quadratic equation or anything like that. The other pole is just S equal to negative Bm plus Bn squared plus Ke squared over Ra divided by Jm plus Jn squared. That would be my other pole in this case. But that pole is going to be guaranteed to be negative, because all of these things, Bm, B, Ke, Ra, Jm, and J, all will be positive. So since there's a negative sign out front, there's nothing that can make it positive. So you're going to have a 0 pole and a negative pole. So this is going to be a marginally stable system. And obviously, if I wanted to do proportional control, like we had talked about before, with the sensor equal to 1 and no disturbances, then my transfer function in that case for the closed loop proportional controller would be Ke over Ra times Kc, where this ends up being your K of your plant, right? And that would be my closed loop control transfer function. And obviously you can you should be able to then take this and find, say, the Bode diagram and things like that for this controlled system, or for the plant system, and things like that. Glad you were able to watch this one, and hope to see you again soon.